Good morning, guys. This is Mr. Fabi. I'm going to show you a little bit about how to do electronegativity. So I'm going to start with a few sheets here. I'm going to bring these up. And on one side, we have a periodic table. Now, this periodic table looks a little bit different from the one that you've seen before. And notice that they have just a single value in each box. So hydrogen's 2.2. If you jump across, you'll notice that helium is actually Na, means not applicable, and I'm going to explain that in a second. And then if you keep going down, you have lithium, beryllium, boron, carbon, and so on. And if you follow the trend here, you're going to see that every number increases just a little bit until you get all the way over here to fluorine, which is 3.98. Conversely, if we look down in the bottom left corner, you're going to see francium. Francium down here is 0.7. So just like we did in our notes a few days ago, francium is the least electronegative element, and then that trend increases as you go diagonally up and to the right to fluorine at 3.98. Now these over here, if you remember, these are our noble gases. These are the elements that have a full outer shell. They have a full octet. And so they have 8 electrons. They are non-reactive. They don't want to react with anything. I know that krypton and xenon do have a value, and that's because under certain conditions you can make them react. But for our purposes, we are going to say that all of these are non-reactive. Okay, these are non-reactive. We're only really looking at column 1 through column 17. You picked up this sheet when you came in here. It says using electronegativity to predict polarity of bonds. And so I'm going to walk you through a couple of these answers here just to get you started. And by the way, this here is our scale. This scale is going to be used on the test as well, so it'll be consistent. You're not going to see anything different on Tuesday. So anyway, part 1. The property of, and you might guess, the property of electronegativity, and I'll underline that for you so you know that that's our first blank, which is the measure of an atom's ability to attract electrons, can be used to predict the degree to which the bonding between the atoms of two elements is ionic or covalent. Okay, so up to this point we've been talking about ionic or covalent. Ionic is usually a bond between a metal and a nonmetal. So those are things here on the left side combined with things on the right side. And so that we would consider those ionic. Covalent bonds are two nonmetals. So you notice the difference between those. If we do a metal over here combined with a nonmetal, notice that we're going to have a very big range in values. For example, lithium is 0.98, whereas oxygen is 3.44. That's a pretty large gap compared to something that's covalent. So if we add something on this side, or I shouldn't say add rather, but if we bond two things on that side and we subtract them, you're going to have, for example, let's say nitrogen and oxygen. If you subtract those, it's going to be a much closer value. If we subtract these, we're going to get 0.4. That's a very small value compared to lithium and fluorine. So this is how we characterize whether a bond is ionic or covalent. We actually have to use numbers. Not surprisingly, in science, we like to use numbers to make sure that we quantify everything. We're not just taking a guess. So you might guess, the greater the electronegativity difference, the more ionic the bond is. Okay, so we're trending toward that ionic side. Let me show you what that means. So we're going to use this scale here. If our difference is greater than a value of 2, we're going to say that's an ionic bond. If the difference between them, okay, we're subtracting, if the difference between them is between 0.41 and 1.99, then we're going to call that a polar covalent bond. Okay, so it's a covalent bond, but it's very polarized. In other words, the electrons are spending more time with one element than the other. And then finally, we have a nonpolar covalent bond. And so because it's nonpolar, that means that these elements are sharing electrons much more equally. The electrons are more evenly distributed. So if you drew the Lewis structures for a covalent bond, you would see the electrons distributed more evenly around the two elements. So let's try some examples here together. We have two elements here, magnesium and chlorine. Magnesium, if you look on your periodic table, is here on the left-hand side. And right here is magnesium. So magnesium has an electronegativity value, again, how much it wants electrons, of 1.31. So I'm going to type in 1.31 in here. And then I look at my second element here, chlorine. Chlorine is way over here in the 17th column. It has an electronegativity value of 3.16. 3.16. Okay, so what you need to do is you need to then either, you can set up the subtraction problem, you can use a calculator, either is fine with me, but if we do that subtraction, 3.16 minus 1.31, we're going to end up with a difference of 1.85. Now I always get the question, does it matter which one you subtract first or which one you subtract from the other? It doesn't matter if you do 1.31 minus 3.16, but that's going to give you a negative number. So if that gives you a negative number, just turn it positive, okay? So if you get a negative number, just turn it positive. You're going to use the absolute value there, which is just going to be 1.85. All we care about is the difference between the two numbers. Now it says bond type here. For the bond type, since we came up with 1.85, and we end up here, this is going to produce a polar covalent bond. Okay, so we're going to write polar covalent bond. I abbreviated. You're welcome to abbreviate. I'm okay with that. Check with your teacher, though, to make sure they're okay with that as well. I will show you a second one if you're still having trouble. If you're feeling confident, go ahead and jump into it. The other one that I want to show you is this hydrogen to oxygen. So we're going to do the same thing. Look on our periodic table here for electronegativity values. Hydrogen, notice it has a 2.2. It's relatively high for ones on this side. And the reason it's so high, if you recall, is because it only needs one electron to fill its inner shell. That inner shell only holds 2 electrons. So what I'm going to do is I'm going to put 2.20 over here, and I'll bold that for you so you can see it. And then oxygen, 3.44. So same thing, we're just going to do our difference. Okay, so if I did 2.2 minus 3.44, I would end up with a difference of 1.24. Okay, again, if you get a negative number, just make it positive. All we care about is the absolute value of the difference. So 1.24. We look up here at our differences, and we notice that 1.24 falls again right here in this range of polar covalent. So this is also a polar covalent bond. Okay. And so that's how you find the electronegativity difference.